Hi everyone, my name is Anna and I'm back with another video today to talk more about Transport 2 or heat and mass transfer. So today I have my agenda listed here on the notes. We're going to derive the 3D heat diffusion equation as if we're looking at a three-dimensional cube, and then we're also going to be showing the temperature profile relationship between a one-dimensional heat diffusion if there is heat generation, and then another part is we're going to simplify the first equation if there's no generation and it's at steady state, rather than just the equation like in its generality. Now we're going to simplify it a little bit if it's at steady state. And use finite differencing to find how that temperature is going to change throughout the cube, and we'll find an expression for that relationship and how the temperature is going to be changing between the different sides of the cube. And then lastly, we're going to plot the third one, that relationship, in Excel, so you can see how the temperature is going to change in smaller increments. So first we're going to start with our 3D heat diffusion equation. So first I'm just going to draw a 3D cube here, just so we can kind of visualize what we're looking at. Alright, I'm actually impressed with myself. That's a pretty good looking cube. So we're looking at a cube here. We're going to go ahead and dedicate our axes. So what's going to be the x direction, what's going to be the y, and what's going to be the z. So we're going to have the x be the one pointing horizontally. Z is going to be our vertical direction, and then our direction going into the page or out of the page is going to be our y. So we just have our axes there, just so we can get good reference. So I'm going to go ahead and label the corners here. Well, actually, I'm not going to do that because that might get confusing. So when we're looking at values for this cube, we want to dedicate the length of the z direction, the length of the y direction, and the length of the x direction, as each having some sort of denotation. So when we're looking at the length in the x direction, for example, we're going to be looking at the change in x. So if we set our initial value as being 0 and then our final as being x, we're just looking at the change in x length. So we're going to denote that as dx. And then dz is going to follow the same suit, and dy as well. So I've just denoted that whole length on the x-axis as dx. Same for the y and same for the z. So we can see that our volume is going to be equal to dx times dy times dz. And this is very important to keep in mind and have dedicated as being that, because we'll be using that in our equations. So when we're looking at the heat diffusion, what we have to keep in mind is that there's going to be some sort of energy storage. So that's going to be the energy that stays within the cube even when there is some sort of heat change throughout it. And then there's also energy generation. So that's going to be any energy that is created within this cube because of any other sort of changes. So I'm going to denote our energy storage as being e to the st. And that's going to be a rate because we're looking at how this energy storage is occurring over time. So I just have that volume is dedicated there, and then the energy storage is going to equal. So we're going to be looking at the density of our object times the heat capacity times temperature. And as you'll recognize, this is very similar to our thermal conductivity and thermal diffusivity coefficients that we've looked at in other videos. So we're looking at the density of our cube because that's very important to tell how the heat is going to get through depending on how dense the object is. Same thing with the heat capacity, how well this material will hold that energy. That will affect the storage. And then also temperature. Obviously, temperature is once again just a foundation to measure heat, not actually associated with energy, but it's a good way to tell how much heat we have, which is equivalent to energy. And this is once again going to be over our time variable, which is going to be dt, so change in time. So that's what I have so far right here. Density times heat capacity times temperature over the change in time. But we are looking at the total volume of our cube. So that's going to be also multiplied times the volume, which is dx, dy, dz. So this is our equation for the energy storage rate. And once again, that's a rate because we are looking at how it changes over time. And now to look at the energy storage, the energy generation. So energy generation is going to have everything to do with our flux. So the flux is once again how much heat or energy is going to be transferred through an object, specifically the heat flux. So depending on how much moves through, that will change how much generation we have within the system. And that's going to be multiplied by our volume as well, because we are looking at how this happens through our system, which is a cube who has the volume of dx, dy, dz. So there's our energy generation term. But each of our net heat flows have to be evaluated in each of the three directions that we're looking at. So since we have a 3D cube here, we're going to have to look at the net heat flow when it occurs in the x direction, when it occurs in the y direction, and when it occurs in the z direction. So I can write that my energy storage equation is going to equal the energy generation plus the net heat flow, which I'm just going to write as NHF, in the x direction, plus the net heat flow in the y direction, plus the net heat flow in the z direction. Our energy storage equation is going to equal the energy storage rate equals energy generation plus the net heat flow in the x direction, the net heat flow in the y direction, and the net heat flow in the z direction. So this is the equation I have here. I've just written that out, denoting each of the directions, because we can't necessarily look at the heat flow in all three directions at the same time. We kind of have to analyze how they change as they move across each direction. So I'm going to go ahead and write this so you can get a little bit of a visualization. So we're trying to see how the heat is going to flow as it moves across the dx area, the dz, and the dy. But we have to find some sort of way to relate our dx to our current position that we're going to be analyzing. So in order to do that, we have to use the Taylor series expansion. You might remember that from Calculus 2 if you've taken that. We're coming back to this, but as a little refresher, Taylor series expansion. Okay, as a little refresher, I'm just going to remind you what that is and how we use that to relate our current position x and extrapolate a further position along some sort of function. So, say for example, we're looking at a function in the x and y. It has some sort of funky curve. Say it looks like this. Has some sort of funky curve. And for example, we know the value at this spot right here. So say we know what that y is. We know what the function equals. So I'm going to say f of x is the same thing as y. That's just denoting what our function is. But we want to find what the value is here at x1. So at x1, we don't know what the y is. So essentially what we're trying to do is just find out what that function will equal when it's at a different position further along its line. So in order to do that, to interpolate, I guess would be the correct term here, we're going to use the Taylor series expansion, which lets you look at a further x along your function that you maybe don't know, but you can use the points that you do know in order to find it. So the f of x1, we don't know what that is. And what that's going to be equal to, or essentially equivalent to, based on the Taylor series expansion, is whatever the function value is at the one that we know, which would be f of x, plus, subtracted by the slope of so that's going to be essentially equivalent to the initial y value that we have at the position that we know, so that's going to be at f of x, plus the slope of the function when we're evaluating it at the position we don't know when it equals the position we know. So we're trying to see what the slope is of our function at the position that we know when it's equal to the position that we don't know. And then that's going to be multiplied by the change in our x's. So x1 minus x. So this is what we have here for our Taylor series expansion equation. The function value of the x, which is the number that we don't know, is going to equal the function value of the x that we do know, plus the change in slope when we're looking at the unknown x value equals the known x value, and that's going to be subtracted by the change in x's. So we're going to want to be looking at this in all three directions because we're going to need that to plug in to our equation that we established, because this is going to be equivalent to our net heat flow. So once again, this is what we have here. So we're going to be plugging this equation in to our main equation with that arrow, and that's going to be equal to our net heat flow once we substitute the function as being evaluating the flux. Because the net heat flow is our flux, and so our function, instead of f, it's going to be q, because we're looking at our function of flux and evaluating that for a net heat flow. So I'm going to go ahead and flip pages over. I'm going to say the net heat flow in the x direction is going to equal, so like I just said before, instead of having our f's here, we're going to change that into our heat flow, so that's going to be q. So q of the x that we know plus the q, which is our function, over, dq, because we're looking at the change in flux or the change in the slope, over dx, evaluated at x equals x1 minus x. So the only thing that we did differently here is plug in q instead of f for our functions. So you've noticed that I've written this in x1 and x terms, and that's what I got from this example right here. But instead we're actually going to substitute in this dx for our value instead. So we're going to denote x as being our starting position and dx as being our final position. So dx is going to encompass whatever position that we want to look at along that x line in our cube, and x is always going to be our initial position. So in order to change this to be more accurate to our actual example, I'm going to do the net heat flow in the x direction. It's going to equal the heat flow at x plus the change in heat flow over change in x when x equals dx. So x is our initial position, which is equivalent to x from this example here. And then the dx is going to be whatever later position we're looking at along our function. So the heat flow, we know what the heat flow is at our x, and we're trying to find what the heat flow is at dx, whatever that position may be. So dx is going to be our extrapolated value. So x equals dx now instead of x1. And then you'll have dx minus x as your change in x value. And we're going to do the same things for our y and z direction. So the net heat flow in the y direction is going to equal the heat flow at y. So y is going to be our initial position now on this cube. So we have our y position now dedicated at the very front, and dy is whatever position we're looking at along there, plus the change in heat flow over change in y, when y equals dy. And then we have dy minus y as our change in y values. And finally, for the net heat flow in the z direction, we'll have the heat flow at z. Z is once again our initial position when we're looking at z there. And then that's plus the slope of our function, so dq, or change in flux, over change in the z direction, evaluated at z equaling dz. And then dz minus z for our change in z direction. So these are the three net heat flow equations that we get now, so these three, and these are accurate to our example that we're specifically looking at. And now we can go ahead and plug that back in to our energy storage equation. So the energy storage rate is going to equal the energy generation plus, now we have our net heat flow in the x plus the net heat flow in the y plus the net heat flow in the z. If you remember from before though, our net heat flow is actually not just this straightforward equation here. So yes, this is a consideration of our net heat flow, but this is actually going to be the net heat flow when we're looking at our final position, because like I wrote this equation here, this is when we're trying to find the value of our final position. So these equations here are actually just our final positions. And if you remember from the other videos, the way for us to find the net heat flow, you have to do the initial position minus the final position in order to find that difference. So I'm going to go ahead and erase this actually. And our net heat flow in general is going to be the Q in minus the Q out. So we'll have, if we're talking about our Q in, that's going to be our Qx term, because that's at our initial position x. What is our heat flow? So that's going to be our in component, because we're going to start our heat flow from our initial position x, and move farther along the block, further into the dx realm. And so our out is going to be what we just solved for, because that was finding our heat flow at the final position, which is where we use the Taylor series in order to find what that value is, using the value that we know, which is at our initial position. So now we'll do minus the final, which is going to be qx plus dq over dx, evaluated at x equals dx, times dx minus x. So that's kind of a mouthful, but it's just copying over what we've already written to find our net heat flow in the x direction. So if we simplify this, we can see that our heat flow at the initial position x is going to cancel, and our net heat flow in the x direction will just be left with negative change in heat flow over dx, evaluated at x equals dx, times dx minus x. And then same thing for our y. Net heat flow in the y is going to be the heat flow in minus the heat flow out, which is equivalent to our heat flow in will be the heat flow at the y position, because that's our initial starting position, minus the heat flow at y plus dq over dy, evaluated at y equals dy, dy minus y. So that's, once again, just copying over our big old equation for our final position that we found earlier, and now we can cancel those qy's out, and we'll get our net heat flow in the y equaling negative dq over dy, y equals dy, dy minus y. Lastly, same thing for our z direction. I'm just going to go ahead and simplify this a little bit quicker, since we already know it's going to follow the same kind of order. So we have our qz minus qz plus dq over dz, z equals dz, dz minus z. So once again, just writing that out, we'll go ahead and simplify this. So our net heat flow in the z direction will be negative dq over dz, z equals dz, dz minus z. Alright, so now we have our net heat flows when we're considering the in minus the out, or initial minus final, and now we can plug this back into our energy storage equation. So now we can add this back into that energy storage equation. So the energy storage rate is going to equal, I'm actually going to put our net heat flows first, and put our energy generation at the very end of the equation. So the energy storage rate is going to equal the net heat flow in the x direction, negative dq over dx. We can actually simplify this part of the equation further. So here we have this equation, negative dq dx, x equals dx, dx minus x. We can actually simplify this into, we're evaluating the change in flux at the x position, as we've denoted at the top here, that x equals dx. So we're evaluating at the x position, and that's just going to be multiplied by dx now. So that will simplify into negative dq to the x divided by dx times dx. And then we'll have plus the change in the y direction as well, so that can be simplified very similarly, plus the z direction plus finally our energy generation. So that's what we have here. We've simplified those net heat flows to just be negative d heat flow at x over the change in x times the change in x, which is that change in x, that dx right there is going to be a position along our x line. And then same thing for our y's in z direction plus the energy generation. And we can go ahead and plug in our known values for the energy storage and the energy generation that we wrote at the beginning here. So we'll have energy storage is our density times heat capacity times temperature all over change in time times the volume, dx, dy, dz, equals, and all of our net heat flows, dq and the x, dx times dx. And then our energy generation term is that flux rate times the volume. Here we have our final equation written out. So just plugged in what we knew for our energy storage over there, and then plugged in what we knew for the energy generation. And the rest in the middle stayed the same. So now, in order to simplify this equation further, we're going to go back to our Fourier's law. So we know that from Fourier's law, our flux is equal to the negative thermal conductivity times change in temperature over change in position, whatever position that we may be looking at. So we want to solve for our flux in each of these positions, because as you see, we have the Qx, Qy, Qz. So we want to solve that in terms of our Fourier's law equation. So Qx is going to equal the negative thermal conductivity, and this is going to remain just K, represented by K, because the thermal conductivity is going to remain the same no matter if we're looking in the X or Y or Z direction. It doesn't matter because the entire cube is made up of the same material, the same density. That's not going to change as we're looking in each direction. So it'll be the heat flux in the X direction is equal to negative K times the change in temperature over change in position, specifically in the X direction, so that'll remain dx. And then our Qy is going to equal negative K once again, dt over dy this time, because our changing position is now going to be in the Y direction rather than the X. And then our dz, our Qz is going to equal negative K dt over dz now, because we're looking at the Z direction. Now we can plug, sorry, I almost forgot. It's actually negative Ka. I forgot our cross-sectional areas in there. That would have been bad. So it's negative Ka times change in temperature over change in position for each of these. So sorry. So that general equation is negative Ka dt over dx. Now we can plug that back in to our equation. So we have the density, heat capacity, temperature over change in time, dx, dy, dz equals. So now we can plug in our Fourier's law equations that we found. So that'll be negative d, and since we're looking at specifically the heat flux in the X direction, we can actually plug in some other variables for our area. So when we're looking at the X direction here, once again, we have our X direction going that way, right? So if we're looking at our cross-sectional area when we're flowing this way, that's going to be made up of our dy going back into the page and our dx going up through the page. So I'm going to shade it really lightly here. So our cross-sectional area, if we're looking in the x direction, is going to be that face right here. And that's going to be made up of dz times dy. So our cross-sectional area, when we plug in our heat flux for the x direction, is going to be dy dz. So we'll have, excuse me, we'll have negative k dy dz, and this is change in times dt over dx. So this is what I have right here. I just rewrote our flux as being in the negative ka dt dx term. So we have negative k, and then plugged in for our area in the y direction is dy times dz, and then that's multiplied by the d over dx, which comes from the flux here, so negative d dx, and then I plugged in the qx. And then on the outside, we still have times dx out here. And then the dt dx in that parentheses finishes off the heat flux from Fourier's law. So we're just going to do the same thing for all of our directions now. Just plug that in. So then we'll have plus negative k, and then now that we're looking in the y direction, our cross-sectional area will be dx dz. So negative k dx dz d over dx times dt over dx times dy. Sorry, these are all negative still. So the negative minus minus. So these are all negative outside of their parentheses because we have the minus here. And then the other minus comes from our Fourier's law equation. So then we'll have negative k. Now in the z direction, we'll be looking at dx dy as our cross-sectional area. D over. I wrote the wrong positions here too. Sorry, my head is in another place right now, I guess. So that's going to be d over dy's instead of dx's because we're looking in the y direction. Apologies for that. So d over dz times dt over dz times dz. So those are all of those net heat flows when you plug in Fourier's law for the heat flux there. That's what that's going to look like. And then we still have to add our heat generation at the very end here. So now we can do even more simplification. So if you notice, in each of these terms, there is dx, dy, and dz in all of them, which is our volume component. So I'm going to go ahead and underline these so you can see it better. So we have our volume component on the left side of the equation, and then you'll notice the dy, dz, and then that dx is actually outside of the parentheses. But you can remove the dy, dz because they don't have any x components. So it doesn't matter that they're being, that it's multiplied by the d over dx because they don't have an x component. So they're actually considered constants in that situation. So they can be removed from the parentheses and added or multiplied to the dx on the outside. And then same thing for the dx, dz, and then that dy on the outside is underlined, and then dx, dy, dz again. And then finally in our heat generation or in our energy generation term, we also have that volume component. So all of these can cancel out, which is great. So what that essentially means is no matter what your volume is of the system that you're looking at, it's not really going to change the fundamental equation that we're deriving here. So you don't necessarily need to know the dimensions to plug that into a volume component. You're going to need some sort of knowledge for your density and your heat capacity, but you're not going to necessarily need to know the volume in and of itself. So now we'll write our density times heat capacity, and we're looking at change in temperature over change in time equals, and now we'll have our negative k d over dx dt over dx minus negative k d over dy dt over dy minus negative k d over dz dt over dz plus the flux rate, which is just going to be Q with the dot over top. So this is our even more simplified equation that we have now after canceling out the volume term. So now we're going to clean up even more. So we can actually divide, so what we're trying to look at here is the change in temperature over change in time. That's what we're looking at here in our energy storage. So we're going to divide both sides of the equation by our density and our heat capacity. So we'll get dt over dx is going to equal, and so if you remember from our other equation, if you have our K value, our thermal conductivity, divided by density and heat capacity, that's actually going to equal our thermal diffusivity component, which is denoted by that alpha letter, if that rings a bell at all. So when we divide our density and heat capacity by each of these terms, we're going to get the K over density and heat capacity in each of those directional components. So we can pull that out to the front and denote that as our thermal diffusivity again. So that's going to be, I'm going to go ahead and pull that negative in front too, so it's going to be negative. Actually, wait, I'm not going to do that. I'm just going to write dt over d little t equals the thermal diffusivity, which is the alpha, times and then I'm going to go ahead and distribute the negatives in front into our equations, or into our parentheses, so this negative will go in here and make it positive. So then we'll have d over dx times dt over dx plus d over dy times dt over dy plus d over dz times dt over dz. And then all of that is added to our flux rate once again. So as you'll see here, I added, so I divided by the, oh, I almost forgot. I divided everything by our density and heat capacity. And so when I did that, I divided the K by density and heat capacity, which is the same thing as our thermal diffusivity, which is represented by alpha. And since each of these terms have that K, I pulled the K out to the front. So if you distributed it in, then you'd still have all of that multiplied by these components. And then I just copied the rest down, d over dx, dt over dx, after distributing the negative in to make it positive, and then lastly added our heat generation term right here with the flux rate over density times heat capacity, since we divided the whole thing by that. Now we can simplify again. So we have dt over d little t equals our thermal diffusivity. And we can multiply the d over dx times dt over dx, since they are common denominators, and get our second derivative for each of these terms. So d squared t over dx squared. So that's the second derivative of the change in temperature over change in position. And that will happen for each of these directions. Plus our flux rate over density times heat capacity. So this is our final simplified equation. So we have the change in temperature over change in time equals thermal diffusivity times the second derivative of temperature in the x direction, y direction, and z direction, plus our energy generation term, which is equivalent to the heat flux rate over density times heat capacity. So I'm going to go ahead and box this in. This is a very important equation to know. Okay, now we're going to talk about the second part of the video, which is going to be talking about the one-dimensional heat diffusion with a generation and how that temperature profile is going to change. So we're going to go back to our one-dimensional example. So I'm just going to show my page is blank again. So I'm going to say example, one-dimensional. So we're going to look at the same example that we looked at a couple of videos ago, where we're looking at some sort of block and one side is going to be perfectly insulated. So if you remember from that, perfectly insulated means that there's going to be no heat flux here. So the Q is going to equal 0, which means that for that temperature profile, the slope here is going to be 0, which I showed in that previous video. And then on the other side, it's going to be exposed to air, so there's going to be some sort of cooling factor on that side. And we're going to go ahead and designate our lengths as being x equals 0 and then x equals L. So this is what our system is going to look like. We have the perfectly insulated side. The heat flux is going to be equal to 0, which is why I've drawn those slope lines as being perfectly horizontal, because the slope is equal to 0. And then the opposite side is exposed to air. So as you'll recall, there's going to be an intense change in slope for the temperature profile as you get closer and closer to our air temperature. So the farther down that we go on that air side is going to be closer to the temperature that the air is at. So when your temperature is higher at the air and it's being exposed to that lower temperature, the slope is going to be more intense because you're changing your temperature more intensely. So the flux is going to be going from the perfectly insulated side to the air side, because we go from areas of higher heat or higher energy to areas of lower heat or lower energy. So the flux is going to go from the right side to the left side, or the insulated side to the air side. So if we wanted to look at the heat diffusion equation that we just derived earlier, this one right here, we're only going to be looking at the x direction because we're doing one-dimensional analysis right now. So that's just going to be change in temperature over change in time equals the thermal diffusivity times the second derivative of the temperature times the second derivative of change in position, plus our energy generation term, which is the flux rate over density times heat capacity. So this is our simplified equation here. Since we're not looking at the x or y or z direction, sorry, the y or z direction, we're not going to have those terms in there. It's just going to be the x direction. Now we want to look at this through Fourier's law because we want to see how this temperature profile is going to change. And in order to see that, we need to look at the slope, which is going to be our dt over dx term from Fourier's law. So Fourier's law is q equals negative ka dt over dx. So this is our normal equation for Fourier's law. The dt over dx is where we get that slope from. But since we're looking at this in terms of our heat generation here, we're going to need to change the flux into our rate. So that's going to be q dot instead of just q. And then we're also still trying to look at this as if it's a 3D object, because this equation is derived in terms of a 3D object. We are just simply looking at it only the heat transfer in the x direction, so we can get rid of the y and z terms. But we're still technically looking at a volume here. It's just going to only be in the x direction. So we need to multiply our heat flux term by the volume. So if we're looking at our system here, I'm just going to denote this as being area. So that block on the side, I'm going to go ahead and shade it so you can see it better. So that piece on the side, that's our cross-sectional area. And then we're going to multiply that by the length, which is the total change in the x direction, to get our volume. So Q times L times A. So that's our heat flux rate times the volume that we're looking at, still evaluated through the thermal diffusivity and then the second derivative of the change in temperature over change in position. Actually, wait, that's not right. Sorry, that's going to equal the negative Ka dt over dx, because we're plugging that into Fourier's law. And our heat flux rate is actually going to be negative as well. And this is because our flux is going to be going in the opposite direction of what we've set our system as being. So we've denoted our x as being on the left side of our system, and the farther we go towards the right, that's increasing our x, but our q is going to be flowing in the opposite direction because it's going to go from higher temperature to lower temperature. So we're going to denote that q as being negative because it's going the opposite direction that we've set our system. So it's negative q dot times the length times the cross-sectional area equals negative Ka dt over dx. And this also makes sense because, as I mentioned before, that dt over dx term is going to be equal to our slope. So if our slope is really high over here, that means that we are farther away from our starting position, which we're going to say that our starting position is actually at L right now, because that heat flow is moving from the x equals L towards the x equals 0 direction. So if we have our slope really, really high, really increased, then that makes sense that that's going to be on this side of our system, because that's much farther away from our starting, which is here, which means that this side has increased as well, because the length here has increased too, because we're farther away from our starting position. So that length has increased, which makes sense for the increase in slope. So now we're going to look at our last part that's going to be separated into two parts. So we're looking at a two-dimensional example now instead of one-dimensional or three-dimensional. And we're going to look at an example that specifically has no generation and is at steady state. And then we're going to use finite differencing to see how this temperature is going to creep in to this 2D block and find an expression for this so that we can plot this in Excel and see it similarly to the way that we did in one of the previous videos. So our example is going to be two-dimensional. So we're going to have something in the X and the Y direction. So I'm just going to draw this block and I'm going to denote this as being the Y direction and this as being the X direction. So I just have my square right now. X is going to be our traditional X axis and then Y the same Y axis. And I'm going to go ahead and rewrite our heat transfer equation. Heat diffusion equation. So that's going to be the change in temperature over change in time equals our thermal diffusivity component, second derivative of temperature over the x plus second derivative temperature over the y plus second derivative temperature in the z plus our heat generation component, which is the Q dot over density times heat capacity. And so as I mentioned before, we're going to be looking at a steady state example that has no generation. And so we can go ahead and actually simplify this equation further. So we can get rid of our second derivative of temperature over the z position because we're not analyzing in the z direction anymore. And we can also get rid of our Q dot over density times heat capacity because that is our heat generation term, and we don't have any generation in this example. So we can go ahead and simplify that and get our dt over dt equals alpha second derivative in the x direction plus second derivative in the y direction. So this is our simplified equation that we have here, and that is now what we're looking at. Now we're going to go ahead and set temperatures at each of our positions. So these temperatures are going to be used when we go to our Excel sheet and look at how that temperature is going to creep in from both sides in the X direction as well as in the Y direction. So our temperature on the sides are going to be, on the left we'll have 120, on the bottom we'll have 1. So our temperature on the left side is going to be 100. On the right, we'll have 200, bottom 250, and top 310. So these are the different temperatures that we're going to start at. These are 1 degrees Celsius, by the way. And so these are the temperatures that are applied at our very outer perimeters. So the top line is going to be at 310 degrees Celsius, and then that'll differ depending on what line we're looking at. So now we're going to start to do our finite differencing. If you remember from the other video, we had to write this in terms of a time component and an x component. But now that we're looking at 2D, we're going to have to add some sort of y component as well. So that depended on, so the time was equal to whatever time variable we were looking at. So that's like our delta t, and then whatever time counter we used. So that was n, I believe. So to find our total time that we're looking at, we're going to do whatever counter we're at times the change in time. So if you remember, like when we were looking at our x, each of those had some sort of dx width between each little chunk that we were looking at, and then at whatever chunk we were at, whatever number chunk, so that the x is denoted by I delta x, that's how we get what our total x is. So we're multiplying however many distances of our chunks times the number of chunks to get our total distance. And that's kind of the same idea for our temperature counter as, or our time counter as well. So we have our delta t, which is just our time intervals times the total number of intervals that we have of that. And then for y, I'm just going to denote that as k delta y. So k is going to be our counter here times the change in y. So if, for example, we were to draw that in our system here, I'm not going to draw it in its entirety, just a small piece. So we have our delta. So we have our delta x and our delta y chunks. So if we're looking there, that's 1/5 of the dx. And so if we were continue that down the row, we would have another piece of dx. So that would be counter number 2, or I equals 2 times the delta x, which is that width. And then same thing in the y direction as well. So now that we have those dedicated, we can also look at our little chunks here. So I'm just going to draw this a little bit bigger just so we can really visualize this out. So this is like that piece that we have in the middle. We're looking at these blocks, each of a width dx in the x direction and dy in the y direction. So let's say, for example, we're looking at this middle piece on the bottom here. We're going to be looking at the temperature at I. I'm actually going to denote our counter for y as being j. Just because, actually, no, I'm going to keep it k. So when we're looking at this temperature here, we're just setting it as our I, k position. So then if we were to look at the block just before it, still on the same level, we would now be looking at Ti minus 1k. So our new position is 1 to the left, so I minus 1, and then it's still at k because we're not moving up and down in the y direction yet. So now, if we were to go just above the initial piece that we started in, we'd be at Ti k plus 1 because we're still in the same x position, so that Ti, but now we're moving up one block in the y direction, so that adds 1 to our k. And then if we were to look at 1 to the right of the Ti k, it'd be Ti plus 1 k because we're moving 1 to the right, so we're adding one more counter, so I plus 1, and the k is remaining the same because we're not moving up and down in the y direction. So now we can go ahead and implement this sort of temperature counter in the x and the y into our equation that we found once we simplified here. So since we're looking at changes in temperature over changes in time, we're going to have our T, I, J be to the n plus 1 because we're looking at changes in temperature over changes in time. So what we want to analyze is how the temperature at one position is changing when the time is changing. Because we're looking at changes with respect to time rather than position on the left side of the equation. And then on the right side of the equation, we'll actually be looking at changes in position, which will change temperature. But on the left side, we're going to be T at position I, J at a time n plus 1, subtracted from the position Tij once again, because we're just looking at the same position, but we're looking at these changes in time. So it'll be the n plus 1 time minus the n times. So that's going to be at one time counter ahead of where we're currently at in time, how is our temperature changing because of that time change? And then we'll just have that still over dt here. So this is what we have for our left side of the equation. So those are in our time counters. And then we can go ahead and write our alpha on the right side. That will not change. And then we can write our changes in temperature now due to position. So the first one that we're looking at is changes in position in the x direction. So we'll have our temperature when we're looking at a position just ahead of where we are at the same j. So it's going to be ti plus 1 because we're looking one ahead at the same j. And that's going to be at any time n minus the temperature at the current position we're at. So that'll be just I. And then once again, still j. So our j is not going to change in this part of the equation because we are strictly looking at changes in the x direction. So the only thing that'll be changing is our y, or our I component. And so that n is going to remain the same as well. And then that will be over changes in the x direction. And then that's going to be subtracted from our temperature at the position we're currently at the same j at any time n, minus the position just behind us now. So I minus 1 at, I'm sorry, I wrote j's. I meant to write k's for our y component. So it'll be I, k, not j. Which I wrote that wrong up here as well. Okay. And then we're still in the delta x. That's going to be over delta x. And then all of that is over another delta x because we're looking at the second derivative here. So we need another change in position. So that's what we have here. Temperature in the x direction just ahead of you minus the temperature in the x direction where you're at, all over that change in x, minus the temperature of where you're at, minus the temperature of the one just behind you, and then that y direction is going to stay the same as the k's, and then that's over delta x, and then that whole unit is over delta x again. And now we're going to look at y component. So that's going to be a similar circumstance, except now we're going to be changing our k's instead of the i's because we're looking in the y direction now. So we'll have ti, so our I is going to remain the same as I. And now we're going to be looking at the y position just on top of us at any time n minus the temperature at the I and the current place that we're at in the y, so that's just going to be k at any time n, divided by delta y minus our temperature at our I, the current k at any time n, minus the temperature at I, the k just below us. So the y position just below us, all over y, and then once again, that is also all over y. So I kind of run out of space a little bit, but you will get the idea here. So this is our y components. So those k's are going to be changing now instead of the i's, and our n's are going to remain the same again too, because this side of the equation is not time dependent the way the left side is. So now we're going to simplify this a little bit. So we'll see that a couple of our
t, I, k variables are going to add together on the top of that right side of the equation. And we're also going to dedicate our delta x's and delta y's as being the same increment. So whether we're moving in the x direction in increments of 0.1, we're also going to be moving in the y direction in increments of 0.1 as well. So those are just going to be equal to each other in order to make this a simpler, more concise equation. So I'm gonna denote that delta x is equal to delta y now, and we'll just write that as delta in general. So our right side of the equation is not going to change here. We'll still have our tik at n plus 1 minus tik at n all over that change in time is going to equal our thermal diffusivity again, that alpha. And so now if we simplify those time components, we're going to see that we actually have 4 different tik variables in here. So I put little arrows to point them out. So we have 4 of them, and they're all negative. So we're automatically going to have a -4 at the position that we are initially looking at. So I'm gonna go ahead and write the other positions first. So we have t I plus 1, k at any time n, plus, because that negative will distribute in and make the ti minus 1 k positive as well, plus our ti at k plus 1 at any time n, and then that negative will distribute in again. Sorry, my throat is super dry. Making it tik minus 1 at any time n, and then a minus that for tik. So all I've done is distribute those negatives into the parentheses and rewritten so that we have our changing x and y temperature positions first, and then our temperature at the position that we're currently at last, because that term is negative. And then if we change all of our deltas into our delta x's and delta y's into deltas, we're going to now get this whole term over delta squared because we have that second derivative there. So the delta x in the denominator with the delta x2, you get the delta squared now because those are going to be multiplied by each other. So this is now our more simplified form. And if we're wanting to go into finite differencing now through the Excel, differencing, I forget how to spell. We know that this system is at steady state. And if something is at steady state, that means that it will not be changing with respect to time. So this on this side, this is always analyzing at whatever time, and since we're not changing through time, we can now set the equation equal to 0. So 0 is going to equal the alpha ti plus 1 k, and we can get rid of the n's now because we're not looking at time anymore, plus ti minus 1k plus ti k plus 1 plus ti k minus 1 minus 4 ti k all over delta squared. So this is our more simplified equation now. So we got rid of those time components and just copied over the rest. And so this is our more simplified form, and we can actually make it even more simplified. So since this is equal to 0, the alpha and the delta squared can also be canceled out because these, if you multiply both sides by the delta squared, that will just disappear because the other side is 0. That'll get consumed by the 0. And then same thing with our alpha. If we divide by alpha to get rid of that on the right side, it'll be once again disappear in our 0. So now we can write this to find the temperature of the position that we're currently looking at, depending on the temperature of the positions around that area. So we're going to set TIK. So that's our current position in the X and the Y that we want to find. And that is going to be equal to the temperature of the position in the X just before it, plus the temperature in the position to the X just ahead of it, plus the temperature of the position just above it, plus the temperature of the position just below it, all averaged out and divided by 4. So this probably seems super intuitive to you and be like, oh, of course it's the average of the areas around it. But we actually had to derive it through this equation. So we have, like I said, temperature to the right and the left, and the temperature above and below, and that's just the average. And that's how we find the current position that we're looking at. Okay, so now I have pulled up my Excel, so we are good to go to show this in Excel and how this is going to work. So we're going to go ahead and start with our initial conditions that we established with the temperature on the different sides of our square. So I'm going to say that our temperature to the left is going to equal, we denoted that as 100, and then temperature to the right is the 200. T-top, the temperature at the top is going to be 310, and the temperature at the bottom is going to be 250. So I'm going to go ahead and make this into equations. So Control Shift F3, and we're going to make these values associated with these letters. And now we're going to make our little square here. So we're going to have this equal T left. And let's go ahead and make this fill. Oop, sorry, I did that wrong. Make this a series, and we're going to fill this down the column until we reach 1,000. Well, actually, let's do 50 because we want to be able to see the bottom. Gosh. I'm so terrible at this. 50. Okay. So, okay. Now that we have our initial conditions, we're going to start by showing our sides. We're just going to make our little grid here. So we're going to have this fill, down as a series, the column until, let's do 15. Because we want to be able to see, actually, I'm going to do a little bit more than that. Let's do like 30 because we want to be able to see all the, oh my gosh, we want to be able to see all of the like sides and everything that we're looking at because we want to see like how it's going to creep in from all different directions. So we don't want to fill it too big, like we don't want to go all the way down to 10,000 or whatever it was that we did last time. So I think I said 30. And now we're going to go by row. Oh my gosh. Series. There we go. Okay. So now this is going to be like our grid. And then we can go ahead and fill this down. Till 29. So that's going to be even with our guy over here, and then we'll fill this. Sorry, this is going to be one. till 29. I guess 28. All right. Oh, I guess I missed one. But this is going to be our little grid that we have here. Is this, let me make sure this is long enough. Yes, it is. Okay, awesome. And then now we're gonna denote this as being our T left. And then this is our T top. Oh, gotta pull that all the way over here. And then this is our T right. Pull that down. And then this is our T bottom. So perfect. I'm gonna delete this side here. Make sure those corners are empty. And so now we have our different barriers with the different temperatures that we're applying here. And we remember our equation that we wrote. So the T at whatever position we're currently at is going to be equal to our temperature at the position just to the left of it, plus, oh, I'm going to put this in parentheses actually, because we're going to be dividing by 4 at the very end. So temperature just before it, temperature just after it, temperature below, or I guess above that would be, and then temperature below it as well. And that's going to be divided by 4 in its entirety. So we can, sorry, that did not work right. Let's go ahead and drag this over. Okay, so I guess that didn't work. Do this whole thing. All right, so now we're going to use our equation to find the temperature of the position that we're looking at. So that was equal to the position just to the left of it, plus the position just to the right. I'm going to add this parenthesis here. Plus the temperature of the position just above, plus the temperature of the position just below. And that's divided by 4. So we get this number here. Now we can go ahead and fill this, but there's going to be an issue. So since all of these cells are blank, it's using its own previous numbers to fill everything. So to fix this, we're going to go to File Options, Formulas, Enable Iterative Calculation. Okay, and so now we're going to get our better answers here. We can go ahead and draw this across here, and then pull this all the way down. So this is kind of how we can see how the temperature is going to progress. So the temperature of the interface between 100 and 250 is going to be less than the temperature between 250 and 200 because these are higher temperatures, so that's going to be a higher number here, and then lower because this is lower, and then we'll see how it slowly creeps in towards the middle, and we can see kind of a little more on this middle leaning left area is going to be lower temperatures here. Because of this lower temperature on the side. So that's just an example of how temperature can creep in when we're looking at a 2D figure. And so yeah, that's going to be it for my video today. Hope you enjoyed.